All right, thanks a lot. Um, yeah, so I'm going to look into what happens in nonlinear computational mechanics solvers. So I'm thinking structural mechanics, possibly with processes like plasticity and damage, viscoelasticity, as well as fluid mechanics, uh, especially fluid mechanics with real gases, so non-ideal gas laws. Um, at a very high level, you can kind of partition these codes into pieces that we could call write once infrastructure. That's a huge lie. The reality is that there's ongoing active research in all of these topics. But it's at least not material specific. And usually that stuff is written by people with a little bit more computer science background, or at least experience and interest. Um, but then there's these, what I'll call high-wear surfaces. So these are things that people who are maybe material scientists, but not without a lot of software development experience. It's often code that's written by students, but not necessarily CS students. Um, and so this is modeling materials, modeling different gases, parameterizing various subgrid processes, dealing with boundary conditions. The list can go on. But my focus today is going to be on materials and equations of state. These others possess a lot of the kind of similar properties. Often we call these things constitutive models. And at kind of a high level, this would be a sort of data-driven pipeline, say, for characterizing materials, but it's representative of lots of other things. So you've got this simulation, a PDE solver in the middle. It might be doing time stepping, solving implicit systems, and it needs some operation that converts quantities like strain to stress. And there's lots of generalizations of this concept, but that's the thing we would call a constitutive model. Constitutive models are often parameterized in some ways. There's a need to evaluate gradients, things like that. Constitutive models are very performance sensitive because at every nonlinear iteration, with some data structures, even every linear iteration, at every time step of the simulation, at every quadrature point in every element of the simulation. This is millions or billions of points per second that are likely to be visited. You have to evaluate these constitutive relations. And if the outer solver runs on a GPU, then you really need the constitutive models to also run on a GPU because it's so data and compute intensive that it would be a prohibitive bottleneck otherwise. Now, at some level, constitutive models are any function, except they're any function that needs to satisfy some properties. So for example, it should be dimensionally consistent. If you were to change the units, say, we're in the US, right? So usually we still use metric, except some organizations like NASA still use the US system. So regardless of what system of units you're working in, you should be predicting the same thing. And additionally, you should have reference frame invariance or equivariance. So basically, this means you could have multiple observers, and we each have our own coordinate system, and we observe the same process. We should be able to agree about what's happening within that process. And so there are some good ways of modeling systems like this. The integrity bases have been very popular for this purpose. And if you design a kind of architecture, it's written here in looking sort of like a neural network, but that's not at all necessary. The idea is you have your inputs, whatever they may be. There may be multiple tensors, and you compute some scalar invariance. And then you have a model that gives you responses to those invariances, a new set of scalars. Those get combined with form invariance. The only thing that you need to change is what goes into this any function box. But that is an extremely active area of research. So there are many papers, certainly in the hundreds realm, per year modeling different materials. And there's a lot of effort that goes into that. And there's also tons of unpublished work related to companies and government work and whatever. And so making constitutive modeling fast and reliable is an important topic. So what's the current state of practice? Material scientists generally like to model in terms of quantities like free energy and dissipation potential. These are scalar valued quantities. They're not observable, but derivatives of those relations are required to have the observable relations, the things that actually run in your code. Further derivatives are needed for efficient solvers. There's kind of two strategies that we see showing up in code. One is to have relatively heavy C++ hierarchies that tend to be very project specific. The other is kind of tedious code written in Fortran. A lot of researchers use commercial software like Abacus, which has a couple of interfaces, UMAT and UHyper. As an example of that, you end up with a Fortran subroutine where you have to return a whole bunch of quantities. And those quantities represent a bunch of derivatives. So our approach is using Enzyme and Diman. I'll get to Diman in a second. Enzyme in Rust is available through this feature autodiff. Right now, that's not merged upstream, but we're in the process. A sample free energy function here is this psi of E, where E is a Green-Lagrange strain. You can implement that. It's kind of like one-to-one with the math expression up on the top, and you get a line like this. And then the observable relation is, say, stress as a function of strain, and you get some model like you see down here, and maybe the important part is sitting there. So this is all nice. These derivatives, including the derivative of stress, is provided just by those autodiff attributes. Diman is a library that was actually presented by Tony Peter here last year, and it provides zero-cost compile-time dimensional analysis. So an example that I'll show here, in gas dynamics, you need to convert between what we call primitive and conservative variables. So here's an example of setting up those structs, and then we convert, and down here is where the equation of state shows up. And we've used an ideal gas law, so you get some relations like these. But this code, imagine it could be much more complicated. Now, we can't currently differentiate a from implementation directly, but you can have a function to do that task. Now, what would happen, for example, if we forgot the parentheses around this piece? So density for a lot of gases is kind of close to 1. If you were dealing with a low speed flow, the kinetic energy would be relatively small. So if you forgot the parentheses and you were working in SI units, you might not notice that the answer is wrong. If you're just using regular F64, you're not going to get any compile time error message when you lose those parentheses. You're just going to get a slightly wrong result, but you might not know that it's wrong. So if you do that kind of thing using Diman, you get this wonderful error message here that tells you the dimension of the thing on the left is different from the thing on the right. There's no other cruft to it. So even a material scientist should be able to understand what's going on there. It also works seamlessly with autodiff. So for example, if I use an incorrect calling convention, I sort of mangle up which of my arguments to, say, this derivative function represent the inputs and the outputs, the primitive versus conservative variables. Then we come down, we get this helpful error message, and it tells us how to get it straight, basically. So the recommendation is correct. And of course, we haven't put any special effort into this. There's no compiler upstream support or anything like that. So this is a meme format that's been around a little bit. So it takes an amazing amount of time to deal with debugging environments and helping students track down errors and helping all the various people who show up on the mailing list and other support forums to figure out what things are going wrong with their code via email or other kind of asynchronous platforms. I am really excited about moving more of these workflows over into Rust. So what I've showed is running within a package called Radel, which is our structural mechanics solver. There is kind of an outstanding issue that we're working on to support implicit materials. So these are used heavily in plasticity and some other areas. They need small nonlinear solvers. Sometimes these are complementarity problems, so it's a root finder or an optimizer. We would like that to be dimensionally aware because there can be lots of tricks to using those solvers well to generate good initial guesses. One of the things that is not supported yet is the custom derivatives for the autodiff feature, because you want to be able to differentiate through the solution of that solver. And there's also a number of things I've been working on in getting GPU support, especially being able to do kernel fusion between portions of a kernel that were originally written in CUDA C and other portions written in Rust. But anyway, I hope to get some of this stuff released in the next few months. I'll go ahead and stop there. Thanks, and maybe I can take a couple questions.
That's great. Thanks so much for your talk. We maybe have time for 1 or 2 questions. There's currently nothing in the chat, so maybe let me start by a question. So you said solver should be dimensionally aware, and then even a chat for linear algebra. And on the slides beforehand, I had been thinking, oh, is there a possibility to actually extend dimensionality to, for example, large block matrix structures where you have different parts of the matrix have different dimensions? Did you think about that?
The issue as I see it is that the dimension needs to be encoded in the type. And for large matrices, like there are many blocks, maybe even not a compile time constant number of blocks, and then you can't put it in the type. So it can become very constraining. The other issue is the types get really messy. So like, imagine you have a 5x5 matrix, but each of the rows and columns corresponds to different dimensionality quantities. That is going to be a very messy kind of compile time message. So I would like relatively simple types, and I'm not sure that it's beneficial for linear algebra kernels specifically. But I think we want to keep the dimensional analysis as much as possible before doing that final reduction, that kind of final lowering to something that is generic linear algebra.